Thank you. So can you hear me?
Very well.
And you can see my slides already.
Yes, also.
Okay, so thank you very much, Patrick, for organizing this mini conference. And I would also like to thank all the participants. So first two talks were really great, and I expect the next one after me also to be great. And what I'm going to do, I'm going to browse a little bit through what we know about the statistical properties of slope to basically let you know why we are interested in these methods. And many of the results which I'm going to show you are the results of my colleagues, not necessarily these are mine results. So, sorry, I have a problem with, okay, yeah, here it is, okay. So I'm going to spend a little bit of time on talking about FDR control, about estimation properties together, and at the end of the talk, I will talk a little more about the clustering properties. So the conference is about slope, so I don't think I need to introduce the slope here. So there are actually two papers on slope which we wrote. The first one is on arXiv in 2013. And if you are interested, I suggest you to look also in this paper. So there are more technical details in the first paper, and there are some parts of a paper which did not appear in the published version in the Annals of Applied Statistics. So here we have slope. As you know, the penalty in slope is constructed in such a way that larger lambdas are assigned to the larger absolute values of beta coefficients. Please, if you have any questions during the talk, please ask them. I will be happy to answer. So why we designed slope? So I have a lot of experience, a lot of in multiple testing. And in multiple testing, we perform many tests at the same time. And a very important notion is a false discovery rate. So false discovery rate, basically, if you, in the LASSO literature, there was a lot of emphasis on the perfect model discovery. If you want to discover model perfectly, you do not allow to have any false discoveries. So false discovery is the coefficient which you find to be non-zero, which in reality is zero. So this is a false discovery. So if you want to have a perfect model discovery, you basically want to eliminate all false discoveries. The price which you pay for this is often a low power. So if you have a finite sample size, if you want your method to not include any false discoveries, very often you also lose the power. So probability that you find a true signal, true X, which is important, might be lower than you might want. So in many fields of science, people are now after false discovery rate control. So in false discovery, when you apply false discovery rate, you allow for some false discoveries to appear as long as they consist only a small proportion of all discoveries. So by V, we denote the number of false discoveries. R is the number of all discoveries. So by discovery, we basically, discovery is any coefficient which we find to be different from zero. So we want to control this false discovery rate, and so we allow some for discoveries to appear, and in return we have some larger power for identifying important effects. And we have an intuition from multiple testing that if we use the sequence of these lambda parameters for slope, which are calculated according to the quantiles, so psi inverse is a quantile of a normal distribution at these significance levels. So if we pick these lambdas corresponds to the very famous multiple testing rule, which is a Benjamin-Hochberg rule. So if we pick these lambdas, we will control false discovery rate. And indeed, we managed to prove it in case when the design is orthogonal. Orthogonal means X prime, X transpose X is identity. So if we pick lambdas in this way, then we provably control false discovery rate. And here is the, so the discovery rate is controlled, as you can see, at the level Q. Q is the value which you choose yourself, like 5%, 10%. And P is the number of columns in our X matrix. So this is a number of regressors, or the number of variables which you have in the X matrix. P0 is the number of these coefficients which are equal to 0. We don't know P0, but we know that P0 over P is small. Not small, but smaller than 1. We know that it is smaller than 1. And in case when we have sparsity, so when there are many non-zero elements, only very few, there are very few non-zero elements in the true matrix, P0 is very often close to P. So this FDR level is close to the assumed level Q. So this is the plot. So this is N and P equal to 5,000. K is the number of non-zero elements in our beta sequence, and you can see that exactly. So the lines corresponds to the theoretical false discovery rate, and the circles are the empirical results. We see basically almost perfect FDR control at the assumed theoretical level. Okay, so this is what we wanted to achieve, and we achieved it in the case of the orthogonal design. So why did we want to do this? Okay, so I told you that there is some gain. If you allow some false discoveries to appear, you increase the power of discovery other, maybe not so strong true effects. What we often want in statistics, we want to have a small mean square error. So mean square error here is measured by the L2 norm of the distance between the slope estimator and the true value of a regression parameter. And in the paper which appeared in Annals of Statistics in 2016, Wei-Ji Su and Emmanuel Candes proved that slope is sharp asymptotically minimax. What it means? So you see here in the bottom, you have so K is the sparsity of a signal. So we minimize this risk over all available estimators. And we find out that this risk is more or less is basically asymptotically equal to 2 sigma squared. Sigma is a variance of the error term in our model. Okay, so let me just recall what is sigma. Sigma is here. It is the. I didn't write the model. Okay, so we assume that our data are generated from the regression model, and sigma is a variance of a epsilon term. I'm sorry about this, that I skipped this definition. So here, sigma k log p over k, this is the minimax rate of the best possible rate which we can attain with any estimator, and slope actually attains this rate. Slope with these, exactly these Benjamini-Hochberg coefficients, what they have in here is actually not exactly this coefficient. You have 1 plus epsilon, when epsilon is some arbitrary constant from 0 to 1. So this is the result, which basically says that there is a gain by using false discovery rate in terms of the estimation properties. And my former PhD student, currently my colleague from the University of Wrocław, proved that if additionally k squared over n converges to 0, then we have a control of FDR. So why we don't have a perfect FDR control? Well, because we are no longer in the situation when the design is fully orthogonal. We have our axis coming from the Gaussian distribution. So the design is only approximately orthogonal. So when p is larger than n, as might happen here, then clearly we cannot have orthogonality. All we have is that the axes are columns in our X matrix can be thought of as a realization of independent random variables. Okay, so these results were further extended by Bell-Leglue and Sybakov to the case when X is a fixed design matrix, not Gaussian, but this matrix has to satisfy some conditions, restricted eigenvalue condition. More or less, you cannot have columns of X to be too strongly correlated. And also they didn't prove sharp minimaxity. So what Emmanuel and Wei-Ji proved is that the minimaxity is sharp. So exactly the constants, this is not only that the rate is k log p over k, but also the constant is 1 here. So with a sharp minimaxity, what Bell-Leglue and Sybakov have shown is rate minimaxity of slope. And this rate minimixity of slope is better than the rate minimixity of LASSO. So if you use LASSO and pick your lambda in a fixed, for any fixed lambda level, the optimal rate of convergence for LASSO is k log p, which is worse than for slope. And for slope, if you pick the sequence according to our formula, then you are going to attain this sharp minimax rate. So maybe very briefly about that the orthogonal design is sometimes occurring naturally. So orthogonal design occurs naturally in case when you want to estimate a function and you use an orthonormal basis. So this is like in the signal processing literature. Orthogonal design is still interesting. And here is another paper which we are still in the process of publishing about robust version of slope. So in this robust version of slope, we use, so in robust version, you basically say that in your data, you might have some outliers. And these outliers, we are modeling by using the mean shift model. So basically, as you can see, we add here identity matrix multiplied by the mu vector. So and this mu vector is sparse. So for some of our observation, we may see some deviation from the normal model. And this model is clearly not identifiable, but if you say that mu is sparse, then you can actually use, so Shi and Owen used L1 penalty. So they basically estimated the coefficients beta and mu by imposing L1 penalty, and you can do pretty well. But what we do, we instead of these L1 penalty, we use here the slope penalty. Slope penalty, separate slope penalty for the beta vector and separate slope penalty for the mu vector. And you can see that when this part corresponding to the mu, if we have a non-zero element in the mu vector, it means that we have an outlier. This part of a matrix is actually orthogonal, okay? And maybe I will just tell you that we have here in this paper, we have again minimaxity results in this robust model for slope. And additionally, we can show that we nicely control FDR with respect to the number of outliers. Again, why do we want to control FDR? So here we have an example when we compare our method in the situation when you have low dimensional setup, so P is smaller than N, and we have large outliers. So what we do, we control FDR. So this is the blue line is our method. So we control FDR and other methods like based on LASSO are even better in controlling. They don't find any false outliers. All methods have large power of identification of outliers because they are large. And in terms of the estimation properties, our method loses a little bit with respect. So here we want to be as small as possible. This is the mean square error of regressors. We are doing slightly worse because we classified some of the observations as outliers, even though they were not outliers. Okay, so we lose a little bit in terms of estimation corresponding to the methods which don't pick any outliers. But here we have a different situation. Here the outliers were small. We are still controlling FDR. We have much larger power than other methods to identify these outliers. And in the results, we are now much better in terms of the estimation properties. So this method basically, as I said, allows you to increase the power of identification of important effects. And in this specific setup, we gain with respect to the estimation properties. Okay, so I told you that we have a kind of a problem with controlling FDR when the design is not orthogonal. So let me just go back to the result of Michałkos. So Michałkos has proved that in the situation of Gaussian design, we can control FDR with our lambda sequence, but we need to impose a strict sparsity assumption. K squared over n converges to 0. And you can see it in here on this graph, which I have shown that we lose FDR control when K increases. So here we have a Gaussian design. We want to have FDR control at the level of 5%, 10%, 20%, and you can see that FDR increases. Okay, so maybe I will skip this one. Now the question is why we have a problem, okay, here. So this is a formulation of a slope so we tried to understand this problem, and we looked more carefully into LASSO, and we wrote a paper actually which appeared in Annals of Statistics with Wei-Jisoo and Emmanuel Candes, where we basically observed that LASSO has also large problems with identifying the true model and what is the real reason for this. So you can represent LASSO estimator in the following way. What you have in the bracket is the true value of a parameter. Then you have the inner product between I, so it should be beta I, sorry, on the left-hand side. So here you have the inner product between the xi column and the vector of errors. And then you have the term which we call vi. And this vi term is like, as you can see, is the sum of the inner products between xi and xj, or other columns. And here you have a bias of the estimator, of slope estimator for this jth coefficient. So if your x's are correlated, and if you have a large bias here, then this term becomes large. And now the problem is that, so this generates additional noise. So if I had know this vi term, I could use, I would have like so for orthogonal design, this vi term disappears, and I can easily select my lambda as to control for discovery rate. Now, because I have this vi term, I have to increase my lambda to control for this extra noise. But now when I increase my lambda, I increase this bias. And this vi term goes again up. So I can only control FDR when the signal is sparse enough, when this bias term is not large enough. So this is, we came up with a heuristic adjustment of our sequence. And here you can see, if we want to control for discovery rate at the level of 0.2, our original sequence decays to 0, like according to this black line. But these two other lines show how these sequences behave. We adjusted the sequence. When n is equal to p, then you can see that the sequence is now flat, basically from a certain point. And here is another interesting situation when we decrease the FDR level. Now it becomes more difficult to control. The sequence, adjusted sequence, actually goes up from this point. And if the lambda sequence is not decreasing, then slope is no longer convex. Okay, so our formula would not be no longer convex. So what we do in practice we basically go up to this point, then flat the sequence, make it flat from this point, and we basically guarantee FDR control only up to this level. So we can control FDR when x's are independent and when the signal is sparse, using this heuristic adjustment. Maybe I will skip this paper because there are not too much time left, I guess, only 10 minutes. So we have several extensions of slope for FDR control. Some things are still in the working phase. Specifically, Michał Kos is now working on the combination of slope and generalized reach penalty. So we actually combine slope and L2 penalty. And we find out that we can relax assumptions for discovery rate control with these methods. We also now use slope for the graphical models and have some preliminary results on the false discovery rate. But maybe let's skip this. A few words, so I have like 10 minutes left. So a few words about what you can do to improve properties, to improve FDR control. Like in case of LASSO, what people often do, they use adaptive LASSO. So in adaptive LASSO, you basically weight each of your betas by the weight which, so if Wi is large, you penalize this coefficient more. So if you have some prior knowledge that beta I is important, you make your W small. If you have some prior knowledge that your beta should be 0, then you make your W large. So what you can do, you can run LASSO initially, like using cross-validation, for example, and get some intuition which betas should be large, which should be small. And then you calculate your W as 1 over F of this initial estimator. And when F is some increasing function. Okay. And now it has been proved that when you use LASSO, adaptive LASSO, like what you see in here, then the range of models which LASSO can find now is much better. What you do, you simply, by weighting, what you do in here, you make this term smaller. You reduce the bias, and you can actually, you don't generate so many false discoveries, so you can identify your model better. So what we did with flow, we did the same. So this is like a very new paper which appeared in Journal of Computational and Graphical Statistics with many co-authors, you can see. So with Wei Zhang, Julie Joss, which was the advisor of Wei Zhang from, Julie was at École Polytechnique at this time. Szymon Majewski and Błażej Masojedów are my colleagues from Poland. Błażej is currently, Szymon is currently a postdoc at École Polytechnique, and he is Weronika Roczkowa from University of Chicago. So I will briefly also, so we use SLOBI. So we have a new version of SLOB when we use weighting. And these optimal weights for adaptive lasso and SLOB, they depend on the signal sparsity and the signal strength. So in our approach, we use a Bayesian approach when we iteratively estimate these parameters. So when we use this adaptive slope, we have to do many iterations of slope. So we reiterate slope by adjusting our weights, and it is really time consuming. So I am very much excited by this conference when I can see an effort in trying to speed up the slope algorithm. And again, what we can see that is the signal. So I'm going to skip, not talk too much about these graphs. So basically, by using this adaptive slope, we can control FDR much better. So here you have SLOBI. This is, so we can control FDR much better and have a pretty good power and good estimation properties, particularly when the signal is strong. When the signal is strong, then our Bayesian methods can learn very well the structure of the signal, and it can adjust very well. When the signal is weak, we have a problem with FDR control when the signal is weak and sparse. So Bayesian methods do not learn so well as we would expect, and we lose some FDR control. But in principle, I believe we are in the process of proving asymptotic FDR control for this adaptive slope version. So here you can see situation when we have very strongly, we have correlated regressor. So rho is not zero, but with a compound symmetry matrix. So all x's which are, for each pair of x's is correlated at the level 0.5. And you can see here that we have almost perfect FDR control and the signal is strong, and we have also pretty good power and relatively good estimation properties. Okay, and a few words about the clustering properties of the slope. So we are now doing the research in two directions. One is basically showing how to pick this lambda sequence to control for discovery rate. We want to debias slope so we can do a better job in control FDR. This is where the adaptive slope comes in. And another thing is very important for us are the clustering properties of slope. So we have already heard from this, from Kentaro, that slope is actually clustering some regression coefficients. So I'm not going to talk about these unit balls for too much. And there's a very nice paper of Ulrike and Patrick in which they identify the patterns or the structure which can be attainable by slope. So what slope can do. And that is a paper which we are now working in the preparation where we provide necessary and sufficient condition for slope for the pattern recovery. So here the order of offer is alphabetical, but in the published version, definitely I will not be the first author. So we still need to decide on the order of authors. So this is a slope pattern, okay? What is a slope pattern? So what slope can do? So slope can identify, so maybe don't, for every vector B in RP, we define its pattern in the following way. So the pattern, okay, so let's go through the example. So here we have a beta vector, and the pattern tells us which clusters do we observe in terms of the absolute value in this vector. So at the so the pattern preserves the sign of beta. So here we have a 0 at the second coordinate, and in the pattern vector we also have a 0. Then we have a cluster where we have 1.5 and 1.5 in absolute values. So this is our first cluster because we order cluster according to the magnitude of betas. And slope can also identify the sign. So, so this is first cluster, but we know that the third coordinate is negative, third one is positive. And also we have cluster number 3. So first and last element belong to the same cluster. First is positive, second is negative. There are many people who want to do the same. So people want to attain clustering by using, for example, fused lasso. I have a question, why do we call it a slope pattern? Why slope is so specific here? Well, because according to the paper of Ulrike and Patrick, what a specific method can do. So we want to do a dimensionality reduction, and the way in which we do this dimensionality reduction depends on the subdifferential of the norm which we are using. And the fact is that the two vectors have the same patterns if the subdifferential of the slope norm is the same for these two vectors. So this specific pattern is actually defined by the slope subdifferential. So this is why slope is specifically designed, let's say, to identify these types of patterns. So I'm not going to, this paper where we do this necessary and sufficient condition is still in the preparation, so I will not show you exact results, maybe like these curves in here. Maybe again, I will skip, so I will not talk in detail about what we see in this curve, or maybe I will talk a little bit. So we have a very strong correlation between, this is a compound symmetry matrix. Axes of diagonal are correlated at the level 0.9. P is 3 times larger than n. Here we have the number of, I think, Patrick, it should be probably the number of non-zero elements, the sparsity of a signal.
Yeah, it's the number of non-zero singular elements.
Yeah, so you can see here, so this line shows the probability that the condition for the perfect pattern recovery of slope is satisfied. And you can see that slope is not so easy for slope to find exactly the pattern, okay? This is, the red line shows also that it is not so easy for lasso to identify the support. So this curve for slope is below the curve for lasso because we want much more. We don't want only to identify the support, we also want to identify the pattern. What is maybe more interesting are these black curves, which basically tell you when a given method can properly sort your beta coefficients. So you can do a post-processing step, cluster things which are close to each other, and then you got a perfect pattern recovery. And here you can see that slope can actually properly sort your beta coefficients under a much wider range of scenarios than lasso can do this. And this is like a simulation which shows a little bit of this. So here is a situation when n is 100, p is 300, I have 25 non-zero elements. Well, lasso can properly, 25 non-zero elements, which are all equal to 5,000. And you can see that lasso can properly separate them, but there is a pretty large, so this is lasso with cross-validation, which has the smallest, basically, mean square error. There is some variability in here and in here. When you use slope, basically all zeros are classified as zeros, and all non-zeros are basically clustered together at the value close to 5,000. Let me just tell you that this is not a perfect clustering. So here, this condition for the perfect support recovery is not satisfied, but you see that the clustering is almost perfect. So you can see visually that you have a much better mean square error than for lasso. Here's another example, which is even much more, let's say, appealing, I think. So we have a correlation. So on this previous example, we had independent regressors. Now we have regressors which are strongly correlated. And you can see that lasso completely cannot separate between zero and non-zero elements, and slope again does a great job. Okay, so in proper identification, so in properly sorted, basically properly clustered the elements. And this is the advantage comes in terms of a mean square error and prediction properties. So here are some results comparing prediction properties of slope and LASSO. And you can see when the regressors are independent. So what you can see in here, maybe let me just try to explain. So here is the sequence of lambdas for slope. We change two things. We change Q and C. Q determines the steepness of a slope sequence. When Q is 0, basically, then it means that we have LASSO. And this white triangle denotes the optimal solution for slope here. And you see that for this specific situation, N and P is 1000, predictors are independent, K is 20. The optimal solution more or less coincides with LASSO. So you use Q, which is basically 0. But when we have more signals, like 100, then you can see that the mean square error of slope, of the optimal solution of slope, is much better than for LASSO. And when the axes are correlated, we already see this for sparse signals. And when the signal is dense, there is a huge difference between slope and Oscar and LASSO. Okay, and as Gian said, we have the application of this in the finance for portfolio selection, which people are really very much in finance interested in clustering. And a few, just last thing which I wanted to say about clustering is that clustering is basically what really drives the clustering. And we have a theorem with Philip Kramer in the paper which appeared in Quantitative Finance this year. Clustering is really induced by the similar influence on your regression coefficient on the loss function. Okay, so what we know from the previous paper of Figueredo and Novak, and from the papers on Oscar, that that slope and Oscar cluster coefficients based on the correlations between them. Now, from the papers of Ulrike, Patrick, and our paper, we also say that there are situations when you can have orthogonal design and slope will still cluster because betas are similar to each other. What really drives the correlation is the influence of x's on the loss function. Here's the theorem. I will not talk about it much. And people in finance are very much interested in because they want to find assets which have a similar influence on the risk of your portfolio. So we basically extensively use this in the context of portfolio optimization. Okay, so what is the future work for us? So we are really, as you can see, probably we are doing a lot of things with slope right now. Particularly, we want to do with adaptive slope, which requires at least several iterations of the slope algorithm. So what is really important for us is to speed up the slope algorithm. And also concerning adaptive slope, the current version which we have goes against clustering. So we want to design a new version of adaptive slope which would encourage clustering, because clustering helps to attain good estimation properties in case when there are some similar regression coefficients in your model. And we actually have so far quite promising results from combination of slope and L2 penalty, and this is what we also plan to pursue further. Oh, this is one more graph from the evolution of a portfolio. So this shows that last sentence. So in the portfolio, you basically want to find the assets so that they minimize the risk of your portfolio. And what you need to do for this, you can minimize this quantity W prime sigma W. If you do it, this is a global minimal variance portfolio. People add regularization term to this to make a portfolio more stable. So, and if you use a very large weight here, then you end up with an equally weighted portfolio. So you put exactly the same money into all assets, and you also gain, and you don't, this is equally weighted portfolio, this is global minimum variance portfolio. If you use regularization with LASSO, you can only reach up to this point. So this is the range of portfolios which you get by LASSO optimization. Basically, LASSO does not allow you to let me just think. Okay, so I know. So what we can do by slope, due to the clustering properties of slope, we can basically reach. So here, in the situation when you don't borrow, so all your weights here in your budget. So this is a constraint when you use portfolio, that the sum of your weights, you basically have a constraint on your budget. So weight tells you how much you invest into a given assets. So if all of these weights are positive, so you don't borrow money, then the LASSO L1 norm is always equal to 1. Okay. So so LASSO basically cannot be used for people who don't want to borrow. Okay, only in this range, when you borrow, you allow some weights to be negative and positive, L1 penalty changes, and LASSO is active. And slope allows you to extend your portfolio by picking the weights from the, by picking different sequences from the global minimum variance to the equally weighted. And this is interesting. So people are exploring it in finance and find out what is the best solution, how to use slope best for the portfolio optimization. Thank you very much. I think I already exceeded my time. Thank you.